In our last unit, we talked about intermolecular forces. We explored the idea that the properties of atoms and molecules can tell us something about whether something's going to be a solid, a liquid, or a gas at room temperature. In this next unit, which is covered in chapters 10, 13, and 14 in your textbook, we're going to explore this idea even further. The question we're going to ask is, how can we relate the measurements that we make in the lab of solids, liquids, and gases with measurements about atoms? We're going to connect the world of atoms and the world of laboratory measurements. Now, I know it's been a while since we've been in the lab, so just to refresh your guys' memory, if you have a solid substance, one of the easiest measurements we can make regarding that solid substance is to record its mass. And remember, the unit for mass is grams. Now, do you remember what measurement device we use to measure the mass? We use a balance. Remember, you have that electronic balance. You put scoops of your sample on the balance, and the balance will read out the mass. The balance is really telling you how much matter is in the sample that you measure. Mass is the amount of matter in an object. Then when we have liquids, one of the easiest things we can measure about liquids or solutions is their volume. Volume is how much space an object takes up. We measure that in liters. Does anybody remember what measuring device we use to measure volume? That would be a graduated cylinder. You have little lines on your graduated cylinder, and given how much space your liquid takes up in the cylinder, you can read how many how full the cylinder is, what line it goes up to. And then we haven't done this in the lab yet, but we can measure the pressure and volume of gases in atmospheres and liters. And again, a sample of gas is going to have a given pressure and it's going to have a given volume, and that's going to tell us how much of a gas we have. Now, whether we're measuring the mass of a solid, the volume of a liquid or solution, or the pressure and volume of a gas, all of those samples that we can measure in a lab contain billions and billions and billions of atoms. Now, the problem is, when we measure these substances in the lab, it's very hard to imagine the billions and billions of atoms that make up the sample. If you take a tiny little grain of salt, that contains billions upon billions of atoms. So how can we go between measurements we can make in the lab and the world of atoms that's kind of difficult to wrap our heads around? How can we measure the number of atoms in the samples we measure in the lab, given that we could never actually count each individual atom, even in the tiniest sample? What scientists end up doing is that they bundle atoms together in these very large bags, you can think. You bundle atoms into bags. One bag of any microscopic particle is what scientists call 1 mole. Now, one of these bags, or moles, contains 6.022 times 10 to the 23rd particles. That's 602 hexillion. It's a very, very large number of particles. And we don't really want to think about that number because that's a really, really big number that we don't want to try to count. But if we bundle every 6.022 times 10 to the 23rd particles into a bag and call that bag a mole, well, moles are a lot easier to count. A mole is kind of like a dozen. It's a way of bundling very large quantities into more manageable chunks. So if you wanted to get 24 donuts, you wouldn't say 24 donuts, you'd order 2 dozen. And if your donut maker already has boxes of 2 dozen, it's a lot easier to deal with 2 dozen donuts than with 24 individual donuts. Same thing with eggs. So a mole is like that, except a mole is a lot larger than a dozen, but it's the same idea. We're bundling atoms into these more manageable chunks. Now you might be wondering why 6.022 times 10 to the 23rd? Well, it turns out that 6.022 times 10 to the 23rd protons have 1 gram of mass. So that's kind of useful, because then that means, remember, a proton weighs 1 atomic mass unit. So that means that 6.022 times 10 to the 23rd atomic mass units are in 1 gram. So the reason we use this number is it just makes, as we'll see later, it makes our unit conversions very, very nice. We define the number so that a mole of protons weighs 1 gram. This number is called Avogadro's number. It was discovered by an Italian scientist named Lorenzo Avogadro. He was the one who discovered this number. And now, if you'll follow the link, there's a neat little video about Avogadro and the mole. If you'd like to click the link and watch that video, it's a good way of reinforcing the concept. Now let's talk a bit about using Avogadro's number. To use Avogadro's number, we just need to know that 6.022 times 10 to the 23rd particles are equal to 1 mole. Well, this fact is basically a conversion factor, if we remember from dimensional analysis in Unit 1. It's a conversion factor that allows us to convert between particles of anything and moles. So, if you haven't figured out, on this slide we're going to do a fair deal of dimensional analysis. If you're thinking, oh my gosh, what's that? I don't remember doing that. Well, you did a little bit of that on the midterm. You did a lot of that in Unit 1. So I would dust off those notes and look over that again. The video should also still be up on Edpuzzle from the beginning of the year if you want to look at that as well. But I would familiarize yourself with that type of problem again, because we're going to be doing a lot of that this unit. So I'm going to do a few example problems. I'll walk you through them because I know it's been a while since we did dimensional analysis, but hopefully by the end of these examples you'll feel fairly confident doing mole conversion problems. If you have 12,345 pigs, how many moles of pigs do you have? Well, normally we use moles to count atoms, but pigs are a bit more familiar, and I think 12,345 pigs is probably more pigs than anybody has probably ever seen in their life, and I include farmers in that. So 12,345 pigs is a lot of pigs. We want to know how many moles of pigs we have. Well, if you'll remember from dimensional analysis, the first thing we've got to do is just write what we're given. So we're given 12,345 pigs. We're trying to convert that into moles of pigs. Well, we have this interesting fact that 6.022 times 10 to the 23rd of anything is equal to 1 mole of anything. So I have pigs on the top. If I bring Sally up, I got to bring Sally down. And then so I have 6.022 times 10 to the 23rd pigs on the bottom and 1 mole of pigs on the top. So then when I do this dimensional analysis, I have pigs on the top and pigs on the bottom. So I'm left with just moles of pigs. If you do that math, it's 2.050 times 10 to the negative 20 moles of pigs. Okay, so that's pretty amazing, right? 12,345 pigs, a ton of pigs, is not even a noticeable fraction of a mole of pigs. But let's see, how many feet do they have? Okay, well, there's a pretty easy way of answering this. I have 12,345 pigs. Okay, in my next block, I've brought pigs on the top, so pigs has to go on the bottom, but feet has to go on the top. So can we think of a way of converting between pigs and feet? How many feet do a pig have? Write that in the form of a conversion factor. Yes, one pig has 4 pig feet. So if I have pigs on the top and pigs on the bottom, when I do this math, it'll tell me how many pig feet I have. Well, that's 49,380 feet. 4 times 12,345. So that's how many feet the pigs have. Then let's see how many moles of feet they have. Let's see if this is a more noticeable number than the number of pigs. Well, I can start one of 2 ways. There are 2 ways I can solve this problem. So I'll do one way. You start with the number of feet that the pigs have. Well, then you say 6.022 times 10 to the 23rd feet is 1 mole of feet. And then that's 8.200 times 10 to the negative 20 moles of feet. But you could also go another way. You could say that, well, I have 2.050 times 10 to the negative 20 moles of pigs. Now, if I have that many moles of pigs, I have 4 moles of pig feet. You know, if I have one pig, if one pig has 4 feet, then 1 mole of pig has 4 moles of feet. If I have a dozen pigs, then I have 4 dozen pig feet. So 1 mole of pigs is 4 moles of pig feet. And as you can see, I get the same answer, 8.200 times 10 to the negative 20 moles of feet. So again, not a lot of feet, or not a lot of moles. Not a lot of moles, even though it's a ton of feet. All right. Now, hopefully you're a bit familiar with how to use the mole, and you've gotten a bit of a refresher on dimensional analysis using those examples. Let's talk a little bit more about how we use this to go between atoms and the real world. So, how many water molecules are in 2 moles of water? So remember, a mole is just a bundle. So let's imagine I have 2 bundles of water, and each one is filled with water molecules, 6.022 times 10 to the 23rd water molecules to be exact. And they want to know how many water molecules are in there. So you start with 2 moles of water. That's 2 bundles of water. Now I think you know what comes next. 1 bundle of water, 1 mole of water is 6.022 times 10 to the 23rd water molecules. Now, I do want to call your attention to this. Sometimes we abbreviate mole MOL, so that's also a valid way of abbreviating mole. I don't want to see anyone abbreviate mole. Oops. I don't want to see anyone abbreviating mole like just an M, because M means mass. Okay, so if you want to abbreviate mole, you can write MOL. But at any rate, the moles cancel out, the moles of water cancel out. And then I have 1.204 times 10 to the 24th, and I made a typo there. Don't ever make this typo yourself. Molecules. Okay, and again, if you want to say molecules, you got to spell out molecules, right? Because if you abbreviate molecules MOL, then you're saying you have moles. So you have to write that molecule out. So 1.204 times 10 to the 24th. That's 2 times 6.022 times 10 to the 23rd. How many hydrogen atoms are in 1 mole of water? Well, now I only have one of these bundles. Okay, but they want to know how many hydrogen atoms are in that. Well, one of those bundles has 6.022 times 10 to the 23rd water molecules. Now, if I stopped here, like I did in my last problem, that would tell me how many water molecules are in 1 mole. But the question doesn't ask about water molecules, it asks about hydrogen atoms. How many hydrogen atoms are in 1 water molecule? How can I convert between water molecules and hydrogen atoms? Well, there are 2 hydrogen atoms in 1 water molecule. So that means that my mole of water contains 1.204 times 10 to the 24th atoms. Now, if you'll notice, one of these bags has as many hydrogen atoms as there are water molecules in 2 of these bags. That should make sense, because each water molecule contains 2 hydrogen atoms, right? So if I have one of these bags, it'll contain twice as many hydrogen atoms as water molecules. So if I have 2 of these bags, it will have the same number of water molecules as there are hydrogen atoms in one of the bags. I hope that made sense. I hope this concept is making sense. If this is starting to make sense to you, you can start on set 1 of your problem set, and there will be more videos to follow. I will see you soon.